Welcome back. Just remind you on your syllabus that shows we have exam 4 coming due in 9 days. Maybe a few people have left earlier for Thanksgiving, so maybe I should send a note out to the class to remind them. But I'm going to put practice problems up on D2L soon in the next few days, and you can look at those in the next week. A week from today, we'll come back and review those practice problems. So try and look at them before then, see if you have any questions. The exam will cover sections 8.1 through 8.4. 8.1 and 8.2 are the law of sines and the law of cosines to solve oblique triangles. 8.3 is polar coordinates, and 8.4 we'll do today on complex numbers. And so you have 9 days to hopefully prepare for all this. Take a look at it. Take a nice time for Thanksgiving, of course. You should have time outside of Thanksgiving to study for the test, since it's a while away. But I wanted you to know over the vacation that I'll be putting up these practice problems so you can get started on them before next class. Okay. It'll be the same thing as last time. All the problems similar to homework, and most of them similar to the practice problems. But today's last topic for that exam is complex numbers, and I probably won't actually quite finish these, so it may just be part of 8.4, I think. All right. And I'm not interested in doing a blistering pace when we're about to go over vacation anyway. So we'll say this, a complex number is a number a plus I times b, in which a and b are real numbers you can write as decimals, right? And I, however, denotes the square root of -1. So that I squared is -1. Wait a minute, there's no number whose square is -1. Well, we just make up one, make a symbol I, and say if you multiply I by I, it's -1. And so we're defining I to be the number whose square is -1, or a number whose square is -1. And because we just made it up, we can call it the imaginary unit. The imaginary unit, or imaginary numbers, actually is a term called coined by Descartes. Rene Descartes, who we said before was responsible. His name goes with Cartesian coordinates. So he was one of the people responsible for generating rectangular coordinates in the plane, whereby you could do algebra problems to solve theorems in geometry. Right? If you take your geometry and put it into the plane and attach real numbers to the points, then you can make an algebra problem out of proving a geometry result. But he became famous for that. He's a good mathematician. He didn't come up with complex numbers, but he did come up with this term imaginary for square root of a negative number. So there's a complex number. It is a real number plus square root of -1 times another real number. In any complex number, we call A the real part of the complex number, and B the imaginary part. Now you think an imaginary part would mean an imaginary number, but no, it means the real number that multiplies the imaginary number, I. So B is called the imaginary part, but it's a real number. And to denote this, we write RE of Z, or real part of Z, is A. IM of Z, the imaginary part of Z, is B. So that's the notation for real and imaginary parts of a complex number. Now needs an example, of course, right? So let's say 3 minus square root 2I. you can actually put the I before or after the number it multiplies. I can put A plus IB or A plus BI, and people write them both ways. It means the same thing. In this number, you can think of this as 3 plus minus square root 2 times I. Let's put the I in front this time. And then this must be A, and this must be B.
Quadratic form.
So then we write that the real part of 3 minus square root 2I is 3, number that doesn't multiply I. The imaginary part of this complex number 3 minus square root 2I is the number that multiplies I minus square root 2. So it's a real number that multiplies I as the imaginary part. All right, so there's an example. Now, in special cases, we can look at a number like this, 5. 5 is actually a real number, right? Because you can write it as 5.000, it's decimal form. It's also a whole number, right? But it's also a complex number, right? 5 can also be written as 5 plus 0 times I, since 0 times anything is 0. And you can say that the real part of 5 is 5, imaginary part of 5 is 0. No imaginary part, it's a real number. Right? So actually what this shows is that the real numbers are a subset of the complex numbers. Any real number like 5 is also a complex number, the real number plus 0 times I. So any real number, A, is also a complex number. We say that the real numbers are a subset of the complex numbers. All right, so a complex number with B equals 0 is real. Also, we can do something like this, minus 3I. We can think of this as 0 minus 3I. And if the imaginary part is 0, we call it a real number. Similarly, if the real part is 0, we call it a pure imaginary number. This one has real part minus 3I is this number 0. The imaginary part, whatever multiplies I, is minus 3. And any complex number, A plus IB, with A equals 0 is called a pure imaginary number. So a complex number with B equals 0 is said to be a real number. Complex number with A equals 0 is said to be a pure imaginary number. Now, what else can we do with complex numbers? This leads into the first part of your homework. And you might say at this point, why do we need these things, right? If they're imaginary, right? But actually, these are extremely useful. And for instance, in engineering, electronics engineers do circuit analysis and other things. So how does the voltage and the current change and so forth? And it turns out complex numbers are a real useful way to figure out the real results for these kinds of things. And quantum mechanics and physics, and the whole thing is built around complex numbers, actually. It's easier to do the math and figure out, likelihood of finding particles here and there if you use complex numbers. So lots and lots of problems in sciences actually use these things to get real results. All right, so now the next topic is this. We'll make a definition. the absolute value of a complex number. C equals A plus IB. I'll put a hack mark here through my Z to show it's not a 2. Is A plus IB is square root of A squared plus B squared. How about that? That seems like an odd definition. Why would we label it that? It actually comes with very good incentive. In fact, it agrees with absolute value of real numbers in the special case that Z is a real number, right? Remember, every real number is also a complex number. So it agrees with the usual definition, and it makes great sense in the following manner. Just as we have a real number line, real numbers, you have number line. And so if we mark on here's 0, and here's 1, and here's 2, and here's 3, and here's 4. Pi is a decimal number, so it's a real number, right? Even though it never repeats, it maybe goes right here, right? Here's pi, 3.14159. Count 3.1 here. And square root of 2 is another real number. It goes on forever. It's 1.414 approximately. So maybe it's about there. Or here's the number 2, right? Those are all real numbers. And if you give me any real number like pi, I can just go plot it on the number line, x, right? It gets harder for complex numbers. Can you imagine? Here's my supposedly, don't write this down, complex number line. And so here's 1. Here's 1 plus 3i, and here's 1 minus 3i. How do I order these things? You know, here's 1 plus 2i, and trying to line them up on a line turns out you can't line them up and make them what's called an ordered field of numbers. So we say the complex numbers just can't be ordered, so you can't put them along a line like that. What are we going to do instead? Well, complex numbers are A plus IB, where A and B are both real numbers. We can make a real number line for B and a real number line for A and make a complex plane. So for complex numbers, instead of a complex number line, we have a complex plane. And one axis for the real part, one axis for the imaginary part. And the idea is just as if you want to plot any real number, you just go over to the spot and order and plot it. Same thing over here. If you want to plot 3 plus 4i, then you go over 1, 2, 3 on this axis, on the A axis. 1, 2, 3, 4 on the B axis. And you say that point, 2 perpendiculars meet, is identified with the complex number 3 plus 4i, just like a point on the number line is identified with a real number. So just like there's a one-to-one correspondence between real numbers, decimal numbers, and points on the line, there's a one-to-one correspondence between complex numbers and points in the plane. And then we call this the real axis, because after all, A is the real part of the number. And if I want to plot like the number 5 plus 0i, here it is. I go 5 in the real direction, 0 in the imaginary number direction. And this is 5 plus 0i, which we can also just write as 5, like we have. Right? So 5 would plot right here. This is a real number. It's in the complex plane. It's also a complex number. Or if I have minus 3i, like we had over there. Let's go 1, 2, -3 on the imaginary axis. And this is 0 in the real direction and -3 in the imaginary direction. So this is identified with 1, 0 minus 3i or so that's how you can plot any complex number. You plot it in the complex plane. This is the real axis. Since this is the imaginary part, we can call this the imaginary axis. And now we can plot all real numbers, just complex numbers, just like we can plot all real numbers. Just we need a plane instead of a line. And now here's where the absolute value comes in. How did we define absolute value for real numbers? If you really think about it, what's the absolute value of pi? Well, it's its distance from the origin, right? What's the absolute value of -2, right? Well, it's its distance from the origin. So absolute value of pi is equal to pi. Absolute value of -2 is equal to +2, its distance from the origin. What if we do the same thing with complex numbers and say the absolute value of a complex number will be its distance from the origin? So if I take any point here, take a point A plus IB, we'd say its distance in the complex plane is this line here. Well, if it's at A on the A axis and B on the B axis, then this is a B by A by something triangle. The distance here is square root A squared plus B squared. That's where this comes from. The absolute value of a complex number will be its distance from the origin in the complex plane. Now maybe you're starting to guess, I don't know. If this is absolute value, that looks like r in polar coordinates, and this angle is theta. Maybe polar coordinates are really useful for dealing with complex numbers, and it turns out that's true. When you take complex powers, I don't know if we'll get to it today or not. Polar coordinates, the polar representation of complex numbers, turns out to be a real useful and easy way to compute powers of complex numbers because of this way we define the absolute value here. But that'll be it. And now, real number absolute value is a special case of complex absolute value. So note for any real number that we say it's distance from the origin, we could define absolute value of x. Or let's say for z equals a plus 0i, what do we get? The absolute value of z is now the absolute value of a plus I0. So any real number z equals a is now has absolute value square root a squared plus b squared, square root of a squared plus 0 squared is just square root of a squared, but square root of a squared, remember, it's just absolute value of a, right? So the absolute value of a complex number written as a plus 0i agrees with the definition of absolute value of a real number a. The idea is that a is a real number, right? Because like if you take absolute value of -2 or square root, let's say, for example, square root of -2 squared is 2, right? This is the square root of 4 is 2 is the absolute value of -2. The absolute value of any real number is the square root of its square, and that agrees with this definition here. When you have a real number, then b is 0, and you get square root of a squared, you get the usual absolute value of real number. So the absolute value of z is consistent with absolute value of a real number. In other words, if z is real, it gives the same absolute value as you had before. So what we've done is we've simply extended the definition of absolute value for real numbers to include complex numbers with this definition, and followed the idea in doing so that the absolute value of a number is its distance from the origin. So now we're using a plane instead of a line. Right? So this underlined complex plane. The complex plane is this plane where you plot each complex number is identified with the point whose real part goes out horizontally and imaginary part goes out vertically. Now we need to do some more examples. That's what I really want you to do for the class, is be able to compute these in your next class. Here's an interesting example. What is the absolute value of 3 minus 4i? All right. This is the first problem in your homework for this section, is compute some absolute values. Not this one, I think, but what is it? According to our definition here, it's the square root of a squared plus b squared, which is 3 squared plus minus 4 squared. This is what somebody's going to do on the test, though. They're going to say, oh, it's minus 3 squared plus 4i squared, and they'll square I. Don't put I in here. It's not this squared plus this squared. It's this squared plus whatever multiplies I squared. So it's the root. A squared plus b squared means the real part squared plus imaginary squared. No I in here. So it's square root of 9 plus 16 is square root of 25 is 5. And indeed, if you go and plot it, 1, 2, 3, 2, 3, 4, 3 minus 4, make your rectangle. This is the point I identified as 3 minus 4i. 5 is exactly its distance from the origin, right? Because of this Pythagorean theorem, 3 on this side, 4 on this side, it's a 3, 4, 5 right triangle. So absolute value of this complex number, 3 minus 4i, is the hypotenuse of the triangle, or 5 units. But you can take the absolute value of pure imaginary numbers. What's the absolute value of minus 3i? I can compute it from the definition and say it's square root. If I think that this is 0 minus 3i, it's 0 squared plus minus 3 squared square root. Well, it's square root of minus 3 squared, square root of 9 is 3. Or here's what's easier in these. You can look at it and tell. Sometimes just being able to look and see is easier. In the complex plane, you just go down and plot minus 3i is down here, right? Did that before. How far is it from the origin? Oh, it's 3 units. So you know what's the absolute value of 3? It's 3, right? Absolute value of 3i is this distance, 3. So you can do it just by looking at how far it is from the origin when it's on an axis. It's really easy. Or you use the definition. Intuition is so much nicer. Okay, so there's absolute values of complex numbers. Well, we need to be able to do arithmetic. After all, they're supposed to be numbers. Well, be able to do some arithmetic with numbers. What's the easiest thing you could do? This is really, really easy except for division. Division isn't hard. What if I want to add 2 numbers? Let's make this definition. If I take a complex number a plus ib, and I add it to another complex number c plus id, let's say the result is add the real parts a and c, and add the imaginary parts b and d times I. So we'll just make that a definition for addition. Easiest thing we can think of. So for example, I take 3 minus 4i plus 2 plus 2i, what do I get? Add the real parts, 3 plus 2, add the imaginary parts, minus 2 plus 4, minus 4 plus 2, and multiply those by I. And it's 5 plus negative 2i, I'll write it as 5 minus 2i. Sum of any complex numbers is again a complex number. We just add the real parts and add the imaginary parts times I. Easy, right? So you can add numbers. And subtraction is similar. All right, if I take A plus IB, subtract C plus ID, I can just make it subtract the real parts, add I times the difference of the imaginary parts. So there's subtraction. And once again, these are consistent with real numbers, right? If these complex numbers have B and D equal to 0, then this arithmetic is consistent with what you did with real number arithmetic. So it makes real numbers arithmetic a special case of this. That's what we want, right? And what about products? What if I want to take A plus IB times C plus ID? What do you think we should do? It's real easy. What we should do is FOIL. That will be consistent with real number arithmetic too, right? So let's try this. A times C, right? First, outside this times this is A times ID. We'll write it in the other order, I times AD. Plus this times this, I times BC. Plus this times this, I squared times BD. And now from our definition of addition, we remember we should add the real parts and add the imaginary parts times I to simplify this. And furthermore, from the definition of I squared has to be minus 1, right? So this is minus BD here, and the result then is AC minus BD. Adding the real parts, this is negative BD is a real number. And then I comes in here, so we've got plus I times AD plus BC. And so we can say multiplication of numbers has this rule, AC minus BD plus I times AD plus BC. Who can memorize that? I mean, you can, but it's not that useful. Instead, just memorize FOIL, right? So complex numbers multiply by FOIL. There's nothing more to it than that. Then there's a very important special case of multiplication. We make the following definition. Complex numbers A plus IB and A minus IB, where one has a positive imaginary part, the other one has minus that imaginary part, and they both have the same real part, are called complex conjugates. They have the same real part and minus each other's imaginary part, we call them conjugates. They have a really great property that when you multiply them, all the imaginary parts fall out. So for these, for complex conjugates, let's ask me lots of questions. I'll go slower that way. I won't finish this much. As you have questions, ask them. For these, suppose I multiply these. A plus IB times A minus IB. No matter what A and B are, they're any decimal numbers whatsoever, any real numbers. What do I get by FOIL if I multiply by FOIL? A times A is A squared, plus this one times this one is, oops, sorry, I needed conjugates. A plus IB and A minus IB. This times this is a squared, this times this is minus IAB. This times this, and then this times this is plus IAB. And this times this is minus I squared B squared. So there's by FOIL what complex conjugates multiply out to. And now you notice that minus IAB cancels plus IAB and you get 0 imaginary part. Furthermore, I squared is minus 1. So this becomes minus a minus B squared is plus B squared. The whole thing is always A squared plus B squared. Where have I seen that before? There it was, the absolute value, right? This is actually the absolute value of Z, or A plus IB, squared. So the complex number times its conjugate is actually the absolute value of the complex number squared. Because this is so important, this complex conjugate concept, we make this following definition. If Z is the complex number A plus IB, then we denote its complex conjugate by Z bar. That will mean A minus IB. Just change the imaginary part to negative, or positive from negative. So that'll be its conjugate. That's an easy thing, right? And then we have our previous result, we have that Z times Z conjugate, A plus IB times A minus IB. So the absolute value of Z squared theorem. We just proved right here. Any complex number times its conjugate is the real number. That's the square of its absolute value. So that's a useful theorem sometimes. And now it needs an example, of course, right? So suppose I take this number again, 3 minus 4i. That's a complex number. I multiply by its conjugate. I just change this one to minus its value. So its conjugate is 3 plus 4i. So the example is Z equals 3 minus 4i. And so I'll take Z times Z conjugate. And what do I get? Well, I get 3 times 3 is 9, right? 3 times plus 4i is 12i. That's first. Outside. Inside is minus 4i times 3 is minus 12i. And last, minus 4 times I is minus 16i squared, or minus I squared times 16, we'll say. I think this is still on. Maybe I better check. But I squared is minus 1. So it's minus is plus 16. This is equal to 25, right? Because these two cancel. The imaginary parts always cancel out. And you get just 3 squared plus 4 squared. 25. This is equal to the absolute value of Z squared, because remember, absolute value of this number was 5 before. It's the side of the Pythagorean, from the Pythagorean theorem. So that's just a verification of this theorem showing that for this special case it works. But it works for any complex number. Take a complex number and multiply by its conjugate, you get its absolute value squared, right? The absolute value of this complex number was 5. An interesting story that actually comes with these. Uh-oh. That's the wrong button here. You might think that these complex numbers come from solving the quadratic equation, right? Because they're really useful in solving the quadratic equation, quadratic equations. But actually, they came from solving third order equations, cubic equations. People needed them for that. It's kind of surprising it came from that instead of what you'd expect. All right, so there's complex numbers, absolute value, and conjugates. Now we're in a place to do division. We've defined multiplication, subtraction, multiplication, addition, and subtraction. How do we define division? Well, it turns out we can induce division from what we've already done. To divide complex numbers, simply multiply the top and bottom by the conjugate of the bottom. And then do division the usual way that you do with real numbers. Multiply the top or numerator and the bottom, denominator, by the conjugate of the denominator at the bottom. That's the way to remember division. All right, let me just do this by example. Suppose I want to find 2 plus I divided by 3 minus 4I. I wonder how that divides. What you can do is write it again. But multiply the top and bottom by the same number so it doesn't change the quotient. But make that number the conjugate of whatever's in the bottom. 3 minus 4I has conjugate 3 plus 4I, nothing more than that. Multiply top and bottom by the same number, doesn't change the quotient. And now, what's the bottom number? We just did it over there, right? We multiplied these out and we got 25. And the imaginary part goes away always, because when you multiply a number by its conjugate, the imaginary parts always cancel. You get 3 squared plus minus 4 squared is 25 by the theorem. But the top, they don't cancel out because these aren't conjugates. You just have to multiply. 3 times 2 is 6. 2 times 4I is 8I. There's first, outside. Inside is 3 more I. And last is I times 4I is 4I squared. But I squared is -1, right? So this is minus 4. The whole last part here is minus 4. 6 minus 4 is 2, combining the real parts. 8I plus 3I is 11I, combining the imaginary parts, just adding them. And the top is 2 plus 11I, and the bottom is 25. Evidently, the quotient of two complex numbers is, these two complex numbers is 2 over 25 plus I times 11 over 25. There it is. Quotient of complex numbers is again a complex number. And you can get it by multiplying the top and bottom by the conjugate of the bottom. Let's try again. Suppose I do something a little different. Let's try this one. This will be for your homework also. Suppose I take 4i and divide it by 1 plus 2i. It's the quotient of two complex numbers, right? Once again, we can do it by multiplying top and bottom by the conjugate of the bottom. So I'll multiply top and bottom both by 1 minus 2i. Conjugate of 1 plus 2i. On the top, this time I FOIL, I don't have a real part here, so I just take 4i times 1 is 4i. Minus 4i times 2i is minus 8i squared. But I squared is negative 1. So the numerator becomes 8 plus 4i. Right? Minus a minus 8 plus 4i. And the bottom becomes, how can I compute this product of conjugates quickly? By our theorem, we could just take 1 squared plus 2 squared. Right? We don't have to multiply this out and FOIL it. It always comes out for a number a plus bi. A complex number times its conjugate is a squared plus b squared, always. So there it is. It's just 5 on the bottom and 8 plus 4i on the top. You can write this then as 8/5 plus 4/5. There's the quotient of those two complex numbers. And you can divide by I even. What is what 1 over negative I is? Well, what's the conjugate of negative I? Think of it as 0 minus I, right? 0 minus 1 times I, if you like. And then multiply top and bottom by the conjugate of this number. 0 plus 1i. On the bottom, what you get is minus I times I, minus I squared. And the bottom, what you get is I. Right? 1 times I times 0. Added. Well, let's see. I squared is negative 1. Negative 1 is 1. So it's just I over 1 is I. Apparently, I and minus I are reciprocals of each other. 1 over minus I is plus I. Kind of an interesting result, huh? So those are homework problems that I'll give you among some others. Look at. And I figure if you can do divisions, you can do all the multiplications, additions, and subtractions too, because after all, we had to do those to do the division, right? So what I'll probably do in the test coming up is give you divisions, and that'll show me that you can also do the other. So absolute value is a homework problem. Division is going to be a homework problem. So let me just go ahead and give those homework problems. Let's just do these for complex numbers for the test. I won't do all of 8.4. Make sure you can do all of 8.3. On the supplement. (8.1) all, 8.2 all, 8.3 all problems. 8.4, make sure you can do number 1. And let's do these divisions, some of which I already wrote for you. 3 minus 2i divided by 3 minus 4i. 4i divided by 1 plus 2i. 1 divided by negative I, what we just did. Square root of 2 plus pi I. This is a 2, not a z in here. Over square root of 6 plus 4i. Square root of 2 over 1 plus I. to try those divisions, and that'll be the end of the test. The following is not for this test, but it will probably be on the final. So. Here's where the polar coordinates come in. They're really useful for complex numbers. For any complex number, Z equals A plus IB, right? Let R be the absolute value of Z, be the square root of A squared plus B squared. We'll just define R to be the absolute value. Remember, that looks like R in polar coordinates, right? It's the distance from the origin, except we'll throw out the negative value too. For the polar form of complex numbers, we'll let R be non-negative. And then, following complex numbers, we'll let tangent theta be B over A. Right, if we had in the XY plane, it was Y over X, there will be B over A since we've got an AB plane. With theta into the correct quadrant, the quadrant of AB. Which means in quadrant 4, this is the arctangent, but in quadrants 1 and 4, this is the arctangent. But in quadrants 2 and 3, it's arctangent plus pi or minus pi, whichever one you prefer. It's the opposite direction. So it turns out that theta will be the arctangent of B over A for quadrants 1 and 4. And the arctangent always gives you the angle in quadrants 1 and 4. But theta is equal to arctangent plus or minus pi, whichever one you want. Because it's always the opposite direction in quadrants 2 and 3. It's over a bit. I'm not sure I'm getting it online. Okay. Whichever quadrant the point is in, that's what we use for the polar representation. Then, what do we get? Because by polar coordinates, remember polar coordinates, how they worked? Always X was R cosine theta. Well, now instead of X, we're using A, so A equals R cosine theta. And we use Y equals R sine theta. Now we have B, so we have B equals R sine theta. We can write for any complex number whatsoever in its so-called standard form, A plus IB. Complex number standard form is just the A plus IB form. We have the Z is equal to A is R cosine theta. B is R sine theta. We can factor out the R and write this as R times cosine theta plus I sine theta. And we call this its polar form. Of the complex number. So every complex number a plus ib, that's a standard form, also has a polar form r times cosine theta plus I sine theta. Now we can compute that for a few numbers here. It really screams for a picture. Let me try and draw a picture. Then it all makes much more sense, right? Picture's worth 1,000 words is really true. Fine. Before I do the example, and so I want to draw the picture. Any complex number a plus ib, what you can do is you're thinking of polar coordinates. This distance r is the distance to the point. We'll now demand that it be non-negative. Before we allowed it to be negative for general polar coordinates. And then this angle, standard position counterclockwise, will be theta. And with this picture in the complex a plus ib plane, we'll say that any complex number z can be written as a plus ib, can also be written as r times cosine theta plus I sine theta, if this is the angle and this is the distance. That's what we wrote on the other side. And it just comes out of arithmetic. If you multiply this times this, you get A. If you multiply this times this, you get B. So it's A plus IB, right? But we just call this the complex form. Now we've got the complex number expressed in terms of this angle and this distance instead of the horizontal and vertical displacements, which is kind of nice for certain applications that we'll see. We won't finish them today. I think I'll save the hard stuff for next time. But we've got that. Now this comes up so often that wouldn't it be nice to have some short notation for it? How could we abbreviate this so we don't have to write cosine theta plus I sine theta over and over? We'll give it this notation. So this is a definition. We'll say that cosine plus I sine theta is also written as cis theta, CIS for cosine plus I sine. So that'll just be short notation for this. Then you've heard of the famous mathematician Euler, E-U-L-E-R. If you, kind of interesting, if you match, there's a mathematics genealogy project. And so you take the PhD mathematician and take their PhD students who under them finish their dissertation and their children, their direct descendants, and then the people who finished finished their dissertation under them or their grandkids and so forth. I'm a 10th generation descendant of Euler, actually. Want to go back 10 generations of dissertations, PhD dissertations. But he came up with this great thing that you'll see in calculus. It's not useful to us now, but I'll give you the notation just for seeing in your other class. We won't use it in this class. Even easier notation is to, instead of saying cis theta, say e to the I theta. And that famous number e, which you saw in algebra, when you took natural logarithm, this is it was to the base e. If you take it to the I theta, it turns out to be consistent with this notation, and you just write this r e to the I theta. So sometimes you'll see this in the literature instead of this. We won't use this in this class, but I thought I'd point out to you, Euler's notation is even easier and it works with the same exponential laws. So you might see it that way in other books as you go along. Just recognize it's cosine plus I. E to the I theta is cosine plus I sine theta. Another notation for it. For your education only. Now, we have this. Let's try this out now. Example, find the polar form of the number z equals 3 minus 3i. How about that? And all this amounts to is doing the same calculations you did with polar coordinates for real numbers, right? You could use polar coordinates for the plane. Well, now we just got a complex plane, but we do the same calculations. what we'll do is we'll say this is A, this is B, A is 3 and B is -3. So immediately by, I didn't write down the thing there, but this is what we use the conversion equations. It's the same as for polar coordinates, except we don't allow r to be negative. We just take the positive version. R is the square root of a squared plus b squared instead of r equals square root x squared plus y squared. And tangent theta instead of y over x is b over a. That converts from the point in the complex plane AB to r theta, the polar form for the number. And then if it's on, if A is equal to 0, then you just look at it and see, just like we said last time. Since you can't do a division by 0, you just look at it in the plane, and the angle is either pi over 2 or 3 pi over 2. And you solve it that way, where you have to pick theta in the correct quadrant, either arctangent or arctangent plus or minus pi. The same quadrant that the point is in, since you're using r positive. Now going the other way, we had x equals r cosine theta, so now we have a equals r cosine theta. And instead of y equals r sine theta, we have b equals r sine theta. And these convert back from the polar form to the standard form. So it's just your same equations, 1 and 2 here, except with x and y replaced by a and b. Easy, huh? You don't let r be negative. Those will convert polar coordinates, a polar form of a complex number, just like they converted polar coordinates for the real plane. All right, so in the complex plane, find the polar form of this one. Well, we just say r is the square root of 3 squared plus minus 3 squared. Be careful on the test. Somebody always says, oh, it's real part squared plus imaginary part squared, 3 squared plus minus 3i squared. That's wrong, right? You take the number multiplying I and square it, you don't put the I in, right? A squared plus b squared, b is the number that multiplies I, you don't include I. So this is square root of 9 plus 9 is square root of 18 is 3 square root 2. That's how far that point is from the origin in the complex plane. Then you use the equation tangent theta equals b over a is minus 3 over 3 is negative 1. How do I get that? How do I get theta out of that? We could say tangent theta equals negative 1, or we just say, well, let's solve it like we did before in the unit circle, right? If tangent is negative 1, I can write that as negative 1 over 1, and then root some square of these is square root of 2, so I'll write that as negative 1 over square root of 2 over positive 1 over square root of 2, or the negative over the negative plus 1 over square root of 2 over negative 1 over square root of 2. Look those up on the unit circle. See, so y could be negative and x positive, right? Negative 1 over square root of 2, positive 1 over square root of 2. We get that point on the unit circle. Or we could get the opposite direction. X is 1 over, y is 1 over square root 2, and x is negative 1 over square root 2. And we figure those angles, since it's square root 2 over 2 or 1 over square root 2 this way and this way. This is a 45-degree angle, pi over 4. Means that symmetry, this is also pi over 4. The angle we want is either this one, pi back up pi over 4 is 3 pi over 4, or this one, 2 pi back up pi over 4 is 7 pi over 4. Now, which one do we want? Since in complex numbers, we always choose r to be the positive distance, we want the one that goes in the same quadrant as the original point. The original point was 3 minus 3i. So we go over 1, 2, oops, let's plotted in the complex plane, A plus IB, we want over 1, 2, 3 in the A direction. A is 3, and minus 3 in the Y direction. 1, 2, 3. And there's the point 3 minus 3I in the complex plane. What we found out is that R equals 3 square root 2. That's how far this is from the origin. But evidently, since we're in quadrant 4, we want this angle. That's this one here, 7 pi over 4. We don't want the 3 pi over 4, we want the 7 pi over 4. That's your theta. So you have to figure out which of these two angles applies. It's the ones that goes into the same quadrant as the original point, since we're choosing R positive. Hence the polar form of the complex number, 3 minus 3I. Let's call this equation star here, star equation. Uh, 3 minus 3I can also be written as R e to the I theta, R times cosine plus I sine. So it's R times cosine theta plus I sine theta. My equation star. Where R we found out is 3 square root 2. And we need to multiply by cosine. 7 pi over 4 was the angle to the point, plus I sine 7 pi over 4. There's its polar form. How about that? So number 3 minus 3I can also be written as 3 square root 2 times cosine 7 pi over 4 plus I sine pi over 4. If you doubt your work, you think maybe you made a mistake, you can always check it, right? Just multiply it out. I just multiply this times this, and you get 3 square root 2 cosine 7 pi over 4. What's cosine 7 pi over 4? You go to the unit circle and say, oh, the cosine is the x coordinate. It's 1 over square root 2. Plus I times the sine of 7 pi over 4 is the y coordinate on the unit circle. It's minus 1 over square root 2. Oops. So cosine 7 pi over 4 is this, sine 7 pi over 4 is this. And now you just multiply it out by, right, distributing. 3 square root 2. Oops. So I wrote too much here. 3 square root 2 right here. Right? 3 square root 2 times cosine plus I sine. 3 square root 2 times 1 over square root 2. This times this plus I times this. 3 square root 2 minus 1 over square root 2. Square root 2's cancel. And I get 3 plus minus 3I. Sure enough, so you just multiply it out and check you got it right? But we call this the polar form. The alternative is to write 3 minus 3I equals 3 square root 2 size 7 pi over 4. Shorter notation. Means the same thing though. Size means cosine plus I sine of whatever number follows. Okay. An application of polar coordinates is an application of trigonometry. Like I say, these are very useful in lots of science problems. Let's try one more where we'll just do decimal. So this was an example. Let's do another example. Let's go back to our favorite number today. 3 minus 4i, what's its polar notation? Well, I'm sorry, let's not do that one. Let's do minus 3 plus 4i. We'll change on that. What is that? What's its polar notation? Well, we figure it out, right? R is equal to the square root of a squared plus b squared is minus 3 squared plus 4 squared, no I in here, right? Oh, I know that's 9 and 16 is 25, square root of 25 is 5. This point is exactly 5 units from the origin. Let's draw it. It really gives you some insight to draw these. 1, 2, 3. Minus 3 on the a-axis. 4 on the b-axis. 1, 2, 3, 4. And there's the point identified with minus 3 plus 4i in the complex plane. To get the polar form, what we need to do is find this distance from the origin. Well, what we just showed is that distance is 5, right? And then we need this angle. So r equals 5 is its distance from the origin. Theta equals what? Well, you'd like to say from the conversion equations, 1. So this is by equations 1. Theta is the arctangent of b over a is 4 over minus 3. And we can do that in decimal form since that's not a special angle. Whenever it yields a special angle, it wants you to do it exactly. But right, 3 and minus 4 does not come from a special angle, so we'll just run it in the calculator. Make sure it's in radians mode here. We want to do radians for these problems in general. You can do degrees, of course. So inverse tangent minus 4/3 gives me minus 0.92729, etc. Sure I get this right. And so we got this representation, then this number is actually equal to 5 times cosine plus I sine of minus 0.927295, is it? Something's wrong here. What's wrong? Move this over a little. What's wrong? The answer is this arctangent isn't right? We have tangent theta equals 4 over minus square root 3, but there's two solutions to that within one rotation. One of them is the arctangent. The arctangent is always the angle in minus pi over 2 to pi over 2. Remember that? So this is actually the arctangent. And so we got the wrong angle. What we want for polar representation is the angle to the point, not the angle in the opposite direction. So what do we need to do? Add pi to get the opposite direction. Theta is not arctangent minus 4/3. It's arctangent minus 4/3 plus pi. Let me add pi to that number. And I get 5 times cosine plus I sine of, let's see. $2.214.297, blah, blah, blah. Here is the polar representation of this number. Because it didn't come out a special angle to that point, we just have to leave this as a messy decimal form, or just leave it as arctangent if you prefer. arctangent plus pi. So therein is the polar form of this complex number. And next time, I hate to start at this time and then come back in a week and look at it. Next time we'll use this polar form. It turns out to be very useful in computing powers of complex numbers. We did arithmetic, right? Addition, subtraction, multiplication, division. What about powers? If you do powers and roots, this polar notation is exactly what you need to make your powers in complex variables easy to compute. But if we start it now, I'll just get it started and have to repeat everything. So let's go have a nice Thanksgiving, and we'll put a few minutes early today. Any questions on what we did here so far? This polar form won't be on the exam. Just stop at the division. Bring some questions on, I'll put all those problems up online and you can bring questions. Hopefully, you're gonna get past this, not too many sections this time.